Number 7 here in our series on sprinting biomechanics is actually one of my own papers. This is a study I did, or published at least, in 2012. This was part of my dissertation when I was a doctoral student and was studying running generally and sprinting biomechanics specifically. I try not to use my own studies in class as much as I can, just because it seems like kind of a conflict of interest, kind of like when you have to buy a required textbook for $300 and the professor just happens to be author of the textbook. But this one's free. You guys don't have to pay any money for this, so at least no financial conflict of interest there. Here we were examining the sensitivity of maximum sprinting speed to the features or the shape of something that we've talked about quite a bit in class, and that's this force-velocity relationship. And so you should hopefully be getting a sense that this relationship, at least in sprinting, has a big effect on performance, that having a force-velocity relationship with a certain shape to it might be beneficial for sprinting performance and could be used to, say, identify, if you can test it in people, could be used to identify like who might be a fast sprinter and why. What we did here, and this was another computer modeling study, was we used a model of the human body here, which was conceptually similar to the other models that we've seen in class, to simulate sprinting. So it's got these muscles here that control its joints, and we optimized the excitation signals sent to those muscles, to get the model to maximize its horizontal speed, get it to sprint as fast as possible. We then systematically repeated those optimizations with the different shapes of the force velocity curve that you see highlighted here in figure 1. And I'm just going to talk about the manipulations we did here in the two panels on the right here, figure 1b and figure 1c. So go ahead and ignore figure 1a here. We're just going to talk about b and c today. B, if you follow along the red line there, is showing the change in shape of the force velocity curve as you move from 0% fast twitch fibers here on the bottom that I'm highlighting, up along the red line here to 100% fast twitch fibers with this line I'm highlighting there. So if you compare the change in shape of those three curves there as the fraction of fast twitch fibers in the model's muscles increases, you can see that it starts to be less sensitive to increases in velocity, at least increases in shortening velocity, in terms of how much strength it loses at that velocity. Okay, with the least flat curve here at the top that I'm highlighting, the one with the most fast twitch fibers, then you retain the largest fraction of possible strength as the shortening velocity increases. Whereas this one here that I'm highlighting at the bottom, the one with no fast twitch fibers, the strength or the amount of force the muscle can produce drops off very precipitously as the shortening velocity increases. Okay. So here representing the sensitivity of the shape of that curve to fiber type fraction, or the amount of fast twitch fibers in the model's muscles. Figure 1c here is also manipulating the strength of the model, but the strength in a specific situation when these velocities are negative. Negative velocities here was indicating eccentric contractions, so contractions where the model was producing force while that muscle was lengthening. So here, by moving up that red line, making it so the model could produce more force when its muscles were being stretched eccentrically. And remember, this was important, or we highlighted this because this relates to that Chapman and Caldwell theory on what limits sprinting speed, where in the late swing phase, my leg has a lot of kinetic energy going forward, and I need to slow it down. I need to arrest that motion and position my foot properly for the next stance phase. And how do I do that? Well, I do this very forceful eccentric contraction of my hamstring muscles primarily, my knee flexors and my hip extensors, possibly explaining why sprinters tend to get lots of hamstring strain injuries, because they need this very forceful contraction of the hamstrings in the late swing phase. So those are the conditions that we manipulated here, repeatedly simulating maximum speed sprinting with different fractions of fast twitch fibers in 1B and different levels of eccentric strength in 1C. Now, why use a model here? Well, these aren't things that we can easily manipulate in human subjects. It's very difficult to go into an individual and change their fraction of fast twitch fibers from 0 to 100. It's very difficult to go into an individual and change their eccentric strength of their muscles by this extent. Okay, we could do like training programs, have people get on different power training and different strength training programs and certain exercises and possibly manipulate these things, but that would be an unknown, right? Some people might respond to the training better than others. Those are difficult studies to control for and isolate these effects, and they're just time consuming and challenging studies to do. So the simulation approach here makes that sort of study in a virtual sense more accessible, less time consuming, and gives us tighter control over specifically manipulating these variables in isolation. So what did we see here? Broadly speaking, changing any of those parameters, so increasing the fast twitch fibers incrementally or increasing the eccentric strength incrementally, increase the maximum sprinting speed of the model. And that's what's shown here in figure 5 in this top panel that I'm highlighting. The red dots are what happened to maximum speed when you increase the fraction of fast twitch fibers, and the green triangles are what happened when you increased the eccentric strength of the muscles. So as we increase those parameters on the x-axis here, the value on the y-axis generally went up. The model was able to run at faster speeds as we manipulated those parameters. What was going on there? Why did it run faster? Which is always the interesting question we should be asking. Here in figure 7 on the left is showing the average forces in the stance phase that the model's muscles produced with progressively greater fractions of fast twitch fibers in the muscles. So white here would be the lowest possible amount of fast twitch fibers, with the bars getting darker and darker, representing a progressively larger fraction of fast twitch fibers, up to 100% fast twitch fibers in the black bars here. And so you can see here that as we increased fast twitch fibers, you see these darker shaded bars increasing progressively in size for most of the muscles. The gluteus could produce more force and stance. The vasti could produce more force and stance. The hamstrings, gastrocnemius, produced more force in the stance phase. So generally our muscles were able to produce more force in the stance phase and produce that force quickly and rise up to that bigger force more quickly when we had more fast twitch fibers here. So supporting the Weyand et al. Theory on what limits speed, the rate of force development in the stance phase, and suggesting the fraction of fast twitch fibers there may be kind of an anatomical underpinning on the source of that speed limitation. Okay, we also saw some evidence for the swing phase theory of the Chapman and Caldwell notion of what limits speed, and this one was a little bit less direct, but down here in figure 8 is shown the average muscle forces that were produced in late swing phase, so towards the end of the swing phase. Okay? And so you might look at this and you say, well, Dr. Miller, here's the hamstring muscles, and it looks like their force, if anything, first of all, wasn't very high and was actually decreasing a little bit as the eccentric strength of these muscles was increased. Okay, so how is that demonstrating what you said, where I got to fire up my hamstrings to limit speed? Notice here what's happening to my hip flexor muscles. Okay? The iliopsoas, this is a hip flexor muscle. It's the primary hip flexor in the model here. And so when I increased the eccentric strength of my muscles, which is what's shown here in these progressively darker shaded bars, the darker the bar, the greater the eccentric strength of the muscles that was being simulated. As the muscles were stronger in the eccentric direction, the iliopsoas, the hip flexor, produced more and more force into the second half of the swing phase. So suggesting it was swinging the leg forward more dynamically, or possibly swinging the leg forward with more kinetic energy, but still able to successfully complete the sprinting motion, indicating that the hamstrings here, the other knee flexors in the model, were successfully arresting that motion, even though the iliopsoas was swinging it forward with greater force and probably doing the swing phase faster and with greater kinetic energy. Okay? So just because we didn't see an increase in force here in the hamstrings doesn't mean that we weren't seeing that effect of the hamstrings being important in slowing down the leg and removing kinetic energy from the leg. That was indeed happening. They were actually removing more kinetic energy. It's just not reflected in the force level here. It's reflected in the model being able to produce more force with its iliopsoas muscles and swing the leg forward faster and more aggressively, because the hamstrings now had a greater capacity to arrest that motion, even if they didn't necessarily produce more forces to, or larger forces on average to accomplish it. Okay, so some support here for both of our theories on what we talked about for limiting speed, the stance phase focused theory from Weyand et al. And the swing phase focused theory from Chapman and Caldwell, suggesting that they share a common underlying physiological mechanism, the shape of the force velocity curve, but are limited specifically by different features of that curve. The shape of the curve on the concentric side for Weyand et al. So this shape over here. Let me get my highlighter out. So this shape over here limiting us in the stance phase, rate of force development, versus the shape on the eccentric side limiting us in the swing phase in terms of being able to slow the leg and remove kinetic energy from the leg. So if you want to determine if somebody is a good sprinter and why, you could measure this relationship on them, which we have equipment that we can do at the joint level in biomechanics labs. Examine the shape of their force velocity curve at their various joints and could possibly figure out, are you going to be a good sprinter, or why are you a good sprinter, or what might you need to train to change the shape of the curve to become a better sprinter. Just some examples of practical utility of information like this. Okay, that is it for that one.